Hello and welcome everybody. Today we are going to learn that it is impossible to put an order relation on the complex numbers. And this was a source of confusion for, I think, many centuries, because people back then, and still today, were and are used to the natural order relation on the real line. Like here, if I have this situation, then of course B is larger than A because it lies farther to the right than A. So maybe it's also possible to have such kind of order relation on the complex numbers. For example, that 2 plus I is larger than 1 plus 1 over 3I, because 2 is larger than 1 and 1 is larger than 1/3. Maybe that's possible, and I think people implicitly assumed that this was possible, but it turns out this is not possible, and we're going to prove that in an abstract way. So, any field is called an ordered field if there is a notion of positivity, meaning that I have a relation that satisfies the following two order axioms, P1 and P2, P because of positivity. There is one distinct element in K, the neutral element of addition. And this relation somehow compares the elements to this neutral element. So, axiom number 1 is, any element of the field must satisfy exactly one of the three relations here. Of course, A can be 0 itself. If not, then either A must be larger than 0, whatever that means, or minus A, the additive inverse of A, must be larger than 0. Exactly one of these three relations must hold. Axiom 1. Axiom 2. Now, of course, we are in a field. If I want to talk about an ordered field, then of course I need to have some connection to the field operations, addition and multiplication. This is axiom 2. If I have two elements satisfying this, A is larger than 0, B is larger than 0, then the sum of both must also be larger than 0 and the product of both. If you think about the natural relation on the real line, this of course is what we are used to. But there are very abstract kinds of fields, for example, fields of functions, where it's not possible to put all the elements on a line. So this could be any relation, yeah? This is just to help you visualize it, but it's very important to work abstractly here. You can't assume that all the elements lie on a line. For example, in the complex numbers, they don't. They lie in a plane. So the set of all elements satisfying this, denoted by P script, are called positive, or the positive elements. And an element is called negative if this holds, if its additive inverse is positive. And if I have such a positivity, a notion of positivity, then it's easy to define an order relation, larger than relation, by saying A is larger than B, if and only if this here defines this relation, if and only if the difference A minus B belongs to the positive elements. And this, of course, in the real numbers is our well-known order relation. Now, a very useful observation is that it follows directly from the order axioms that any field element in an ordered field that is not a 0 satisfies A squared lies in the positive elements. I try to avoid using larger than 0 because it always gives you the image that it lies on a line to the right of the number 0, which it doesn't have to be true in most cases. So, we proved that by P1 there are only two cases. A is not 0 by assumption, so either A is positive or A is negative. If A is positive, then A squared, which is defined as A times A, is by axiom 2 positive, because A is positive and A is positive, so A times A is positive. That's it. That's the easy case. Now if a is negative, meaning that minus a is positive, then we use this relation here, which we actually proved in the last video. This is not self-evident. You actually have to prove that, which is not as easy as it seems, because you're used to that minus times minus is plus. But you have to deduce this from the field axioms. See last video, a squared is minus a times minus a, but these two guys are positive by assumption. So again, by P2, the product is positive. And that's it. And now, using only this and the order axioms, of course, we can prove that it is impossible to have a notion of positivity on the complex numbers that is consistent with these two axioms. Now, of course, you can't verify this directly by saying, okay, I tried 17 notions of positivity, none of them works, so there is no. That would be nonsensical. So this cries for a proof by contradiction. We simply assume there is a relation satisfying these two axioms on the complex numbers, and then from this we deduce a contradiction, which here is very, very easy if you know how to do it. We take the complex number 1, the neutral element of multiplication. Then 1, of course, is 1 squared, because 1 times 1 is 1. That's the definition of 1. And now, by our little observation here, this is positive. Okay? So far we haven't used anything about the complex numbers. Now, minus 1, and this is the important idea, which in the complex numbers can be written as I squared, and I obviously is not a 0, gives minus 1. But then again, by this observation, minus 1 equaling I squared must also be positive. And this directly contradicts P1, because now we have a number 1 that would satisfy both relations, which we cannot have. So we have a contradiction to P1. And this proves that no matter how tricky, how fanciful your ideas are for defining a positivity on the complex numbers, it can't be true that it satisfies these two positivity axioms. Chalk drop. See you later.